am really honored to be here to present our research. It's done by my PhD student, Zhao Cai, and me, and also my two colleagues at Utah State, Anthony and Song Q. So the title of the presentation is Exploring Bicycle Route Choice Behavior Using Space Syntax. The motivation of this study is we all know bicycle is a critical component to livable community. And cycling is good to your health, cycling is good to the environment, it reduces emission, it reduces VMT. However, in terms of the cyclist road choice behavior, we don't know a lot of information. We know that route choice of cyclists is influenced by many factors, and but however, if you look at literature, you can see that travelers' cognition understanding of the road network has been overlooked by previous studies. And we also found that space syntax theory has been used by other researchers to investigate travelers' cognitive understanding of the network. So we decide, well, why not we use the space syntax theory to investigate cyclist route choice. And even more, we think, well, it probably is not sufficient to just use space syntax theory, because space syntax theory is totally spatial analysis. That's just a topological analysis. And we figure, well, we should also include other bicycle-related attributes that we can improve the model further. So that's the motivation of this study. And if you don't know space syntax, perfectly fine. I will talk a little bit more on the background about space syntax. So this is theory first proposed in England in 1984. And originally it is used by architects for modeling people's movement within a building. Okay, the basic idea is people by space syntax theory. The theory is people don't. Well, when people make their route choice, they don't care too much about the distance. What they do care about, or very sensitive to, is the space changes. Okay, so give you one example. Within a museum, let's say, if you can see something, then you perceive that is very close to you because you can see them directly. But let's say there's another exhibition very close to you, but in another room, you cannot see that directly. You perceive that's relatively far from you because you cannot see that directly. So it involves one space to another space. There's space change. So whenever there's space change, you perceive it's a little bit further away from you. So that's the basic idea of space syntax theory. And it has been successfully used in urban planning, transportation, and also spatial analysis, human interaction, etc. So this is a key step of space syntax theory. That is, you need to construct something called dual graph. So this is a key point. It's totally different from our traditional transportation analysis. This is a network, road network. In traditional transportation analysis, we will use the road as links and intersection typically as node. That's what we do, right? When we abstract a road network from this road network to this more abstract transportation network. However, in space syntax, we do the opposite way. In space syntax, the street, okay, this is, let's say, street 1, street 2. So in space syntax, street will become node. So this street 1 become node 1, street 2 become node 2. And intersections now is represented with links. For example, you go from street 1 to street 2. So that's from space 1 to space 2, right? Then there involve two turns. Turn here. So that means you have two links, right? So look at from node 1 to node 2, you have one link, two link. So you can also turn here, you got two links, turn here, got two links. Okay, so the biggest difference of space syntax is the way you construct the network. Okay, so just totally opposite way we traditionally do in transmission analysis. Okay, so with this graph, you can actually measure how far away from one street to the other street. Okay, so if you have a measurement or if you have an indicator somehow that can measure the distance, or we call step in space syntax, if you can measure the distance of steps from one street to all the other streets in the entire network, if you can do that, that's essentially some kind of a proxy to accessibility. Make sense? So that's exactly what we're going to do here. And this is just some new development about space syntax. The traditional space syntax think any turn will be one step. So any turn, doesn't matter what is the angle, it'll be one step. And then a newer theory basically says, well, every turn doesn't have to be equal. So you don't have to have one step when you have this perpendicular 90-degree angle. When you have a small angle, a step can be less than one. So it can involve decimal point. So this is some new development of the space syntax theory, and that's the one we're going to use. And I talk about accessibility, right? So we just need to find some indicator somehow can capture this accessibility of one street to all the other streets in the network. So in space syntax, we call integration. Okay, just think about this as an indicator that tell you what is the accessibility of one street to all the other streets. So we got two different type of integration. One is called global integration. The other one is called local integration. So global integration simply measure the accessibility of one street to all the other streets in the entire network. Okay. For local integration, instead of looking at entire network, we only look at a small portion of the network. Okay. Why we do that? Well, think about pedestrians. Okay. For pedestrians, they can't walk very far. So they don't really care about the accessibility of the entire network. They will only care about their neighborhood. Let's say 3 blocks or 5 blocks, right? They don't really care about, okay, whether my street, a particular street, is very highly accessible in the entire network. Well, it's not their concern. They only worry about their local integration or local accessibility. So there's two different types of integration measurement we're going to test in our analysis. Okay. So here's some literature review of a space syntax theory and its application in transportation. So you can see that it has been successfully implemented in different modes: vehicular traffic, pedestrian traffic, and also bicycles. Okay, and by looking at the literature, we found that there's a trend here. The trend is for vehicular traffic. Okay, people use global integration more when they describe the accessibility of the certain space or certain street. Okay, that does make sense because vehicle can cover a bigger area, so typically entire network, right? But when you look at pedestrian traffic, typically people will use local integration. That also makes sense because for pedestrians, you can't walk very far. So you only worry about your local accessibility, so that we use local integration. For bicycle, we identified that it's a gap in the research. We don't find many research using space syntax to investigate bicycle traffic. There's only 3 studies, and we figured that the results are not ideal. The reason is space syntax analysis is essentially a spatial analysis. It doesn't account for many transportation-related attributes. So we figured, well, we will do this similar study to this 3 previous study. However, we will add bicycle-related attributes to the model. So that's the idea. And in terms of the methodology, well, it's relatively straightforward. We will use linear regression to investigate the relationship between bicycle volume and various attributes. So the various attribute here includes space syntax measurement, and also bicycle-related other attributes. So I will talk about all these other attributes. So here, first one, link cognition. So this essentially is the space syntax measurement. It will be either global integration or local integration. This one describes cyclist perception about the link accessibility within either the whole network or within their neighborhood. Okay, and then we include 5 additional attributes here. That's bike-related, include bicycle level service. That's extracted from basically based on Highway Capacity Manual 2010. We also include motor vehicle volume. We also include link pollution, whether you have a cycle lane or not, and average slope. So we think those 5 additional variables may contribute to cyclist route choice decision. So we did a case study in Salt Lake City. The data collection was done in 2015 and in the month of September. Totally, we collected bike count in 19 intersections. And for each location, we did bike count for 5 days, 2 days, 2 hours each day. So totally, we got 95 2-hour bike counts. Okay. So here's a map showing all the locations of the bike count in Salt Lake City. So if you're familiar with Salt Lake City, you can see pretty much cover all the downtown area, and including this is the University of Utah. It's sitting on the east bench of Salt Lake Valley. So this basically it's a hill, and all the remaining part are pretty much flat. So before we can do the regression analysis, first thing we want to do is we need to run the space syntax analysis. So we did both. We did global integration and local integration. As I mentioned, global integration is a measurement of the accessibility of one street within the entire network. And the local integration is just within the neighborhood. Okay? So when we did the local integration specifically, we used 3 kilometers as the radius. The reason is we figure cyclists, when they do cycling, they don't travel very far. If they go beyond 3 kilometers, that's about 2 miles, then the percentage of cyclists just drop dramatically. So that's the assumption we make with 3 kilometers when we calculate this local integration, or you can call this local accessibility. And then if you compare these 2 maps, and you can see this map has a warmer color. That basically means the street here has higher accessibility. The reason is because you're considering the entire network. So obviously, all the street can go to more places. So that's why you see the color is warmer. And this one, the color is colder, so you can see more blue here. The reason is we're only considering the local integration. We only consider 3 kilometers, basically 2-mile radius. Okay. And the other data for the other dependent variables we collect from various sources, including Utah Department of Transportation, Salt Lake Transportation Division, and also Utah ARGC. Okay. Other variables, some of them we won't be able to get, then we estimate based on Highway Capacity Manual 2010. So the first thing before we can do the regression analysis is we need to answer a question: which space syntax measurement we should use in our regression analysis? I mentioned there's 2, right? We have a global integration, we have local integration. Our feeling is we think, well, in local integration actually makes more sense because cyclists are very similar to pedestrians. You won't be able to travel very far. So you probably don't care about the link accessibility within the entire network. You probably is more concerned with your neighborhood, right? So we run this test, and we found that that's actually true. We construct 2 models. One is called global integration model. One is called local integration model. And we found that the integration variable in the global integration model is not significant. However, if you look at local integration model, it is significant. And if you compare the R-square value the R-square for the local integration model is much higher. So we figure that's our assumption is kind of correct. So we will go with the local integration measurement in the regression model. So when we construct this regression model, we just include, because we don't know which variable will be significant, so we just include all the 6 dependent variables, and we run this model using this the field data we collected, and we found that, well, the model is pretty good. The R-square is relatively high, over 0.7. However, if you look at the individual variables, many of that they are not significant. Okay, so what we do is we start to kicking off those insignificant variables, and we end up with this final model. So in the final model, you can see there's only 2 variables. Okay, one is the local integration variables, and the other one is the motor vehicle volume. Okay, and if you look at this, first of all, you look at the statistical value here is all significant at 95% confidence interval. And if you look at the sign of here, so the sign associated with integration is positive. That simply means cyclists prefer links or road segments with higher local accessibility. That does make sense. And look at this sign. The sign associated with motor vehicle volume is negative. That simply tells us cyclists do not like cars. They will choose street with less cars. So that's just very similar, well, just confirm our intuition, right? So, but interestingly, if you look at this model, there's this couple variables we thought they should be significant, but they're not. For example, bike level service and pollution, and also the bike lane, whether you have bike lane or not, and also slope. We thought those should be significant, but they're not in this model. Okay, this couple explanation and implication we are going to talk about after this slides. So in summary, what we did is we did a real-world case study in Salt Lake City to demonstrate the model we proposed. And what we found is the space syntax measurement here specifically is a local integration can explain bicycle volume pretty good. By incorporating another bicycle-related variable, here we include the motor vehicle volume. The model can improve its explanatory power pretty substantially. And it kind of confirms our motivation, right? We want to combine space syntax measurement with other bicycle-related attributes, and we want to build a model that has higher significance. And it kind of confirm our motivation. We actually can do that. However, I want to talk about the limitation of this study a little bit, if I got a couple more minutes. So as you can see, the sum of the variables we think that should be significant, but they are not in our model. Well, the explanation is, first of all, we have a very small data set. We choose 19 locations, and we did data collection for 5 days. Well, the reason is bicycle count is very difficult to get. It's not like vehicles. You have a very good loop detectors you can deploy, but for bicycles, it's always difficult. So we use manual count. So that's limited our data set. That's one thing. The other thing is, in the model, you can see we don't include any demand-related attributes. Okay, that might explain some of the variable why they are not significant. I'll give you one example. Remember in the map here, this part. This is the University of Utah. So University of Utah sits on the east bench of the valley. So you would expect that because it's on here, so less people would like to ride a bike up here. So you would expect that the bicycle volume should be lower. However, because U of Utah is a huge activity center, right? It's a huge trip production and trip attraction zone. So people will go to U of Utah regardlessly. Well, it doesn't matter whether you have a slope or not, right? So, but in our model, we're not able to capture that. We don't have any variable capture the demand or heterogeneity in terms of the chip production, chip generation. So that's why the slope variable here is not significant. So that's why we think, well, we should be very cautious about drawing a quick conclusion, say, pollution and also slope is not related to cyclist choice. Well, we shouldn't jump to the conclusion very quickly because there's some limitation in our methodology. And in a future study, we would like to incorporate more demand-related attributes, and hopefully we can get more bigger or more points so that we have a bigger data set so that we can run a more robust analysis. And that's pretty much what I have today. Thank you.